And hello again, young gentlemen. We continue to talk about flight controls. But right now, in front of you, you see the whole chapter in this pilot book that I already used for illustrations, which is called Flight Controls. But to be truth, flight controls are also a bit, at least explained, aircraft construction, aircraft structure, supposed to be in English. I afraid the book was written by someone who is not native English. Uh, no, and this book is really it's not for engineers. It's for pilots and for those who have zero knowledge actually about aerodynamics, about everything, and it's very similar to the first year students. To be frank, no, at least we pretend that you are still first year students. You know nothing, and we are studying everything like from zero. Once again, we are talking about flight controls. uh, General picture of airplane that we usually use so-called conventional aerodynamical scheme. It means that it consists of fuselage, wing, stabilizer and fin, which suited behind of the wing, after the wing at the rear fuselage, so called. You see here, I opened the picture on purpose in order you see this weird word empennage. Empennage, as I said you, it also comes from French, and in English you might meet in different sources also tail unit group. Tail unit group or empennage, it's include both stabilizer horizontal and vertical, I mean fin, and all the so-called mechanization, so control surfaces on different edges of these stabilizers, whether it's horizontal or vertical. You already know that one which placed at the end of stabilizer, it's called elevator because it's responsible for elevating airplane up and down. Actually, I even took some pictures already to slides in order not to show, not to search for them long. What you see, elevator. Uh, how it's physically arranged in airplane. In cockpit, pilot has either so-called control stick or control wheel. No, in big airplanes where it's lots of space of cabin of cockpit, it's control wheel. In limited no dimensional conditions. I mean, little airplane, military airplane, usually it's just control stick. And also pedals, we will see it in the next picture. And these three main motions, they are realized, no, like the motion on hand and legs of pilot, they are natural. It's somehow similar like into automobile we get used to. Front, no control stick, front, back maybe moved, right, left, and intuitively it corresponds to our understanding like control stick front or steering wheel downward. In this case, maybe it's pitch down, nose down, no? Control stick to yourself backward, or if we pull wheel to yourself, it's pitch up, nose up, and tail down. And right, left, quite clear, and pedals also. It's no, it's like it's understandable for us. We may imagine it. The whole system. What right now you see illustration like with mechanical control system. I mean, interface between this control stick and the elevator, how they interact. Here it's shown mechanical system. Do not pay any attention to this fact. It's not the subject of our conversation right now. Mechanical system, maybe hydraulic system, maybe pneumatic system. No, in some classes we talk about. But most popular by now is so-called fly-by-wire system, electrical system, which combined with some mechanical devices responsible for applying the force to surfaces. Quite clear that electrical signal is not able to rotate elevator, for instance. We need some force to be applied, and in this case we have electrical wires, electrical cables, and special electrical machines, so-called boosters or actuators, which are responsible to applying for applying the force to these elevators and so on and so forth. Once again, how it looks like in general, no, maybe not the best picture, but bright one at least. You see, no? For motion in a different direction, in cockpit we have stick and we have pedals. Now here it's helicopter. In helicopter case, it's a little bit more complicated. And once again, very beautiful picture, thanks to those who developed it. You see all these three motions and three types of control surfaces which are responsible for these three motions. Here it's given a little bit with simplification. What is simplification right now we need to talk about. In our conversation previously, we stopped that aileron is responsible for rotation, it's used for rotation of aircraft along its longitudinal axis. But it's not quite true. What is not true, we will see right now. No, look, here I said it's a bit simplified in explanation. For explanation next, we need three-dimensional picture. I'm not satisfied with this three-dimensional picture. You will understand later what with, but anyway, grateful for this picture. It's help us to understand something, to imagine. Look, in one half of wing, aileron moved down. In another, you see, no, closer to us at the left half wing, it's moved up. What it resulted in? As we spoiled here the curvature of airfoil, we have less lift here. Here we have more lift. Here we have less lift. What happened? Like left wing, what this left wing, like it's fall down right now. Agree? But also, what we did here, besides of we reduced the lift here, what we did? We increased the drag. Really, we spoiled the shape of the wing in this place, and dearly and quite clear in this place we increased the drag due to this. Now, in this picture you see, in my opinion, it's wrong. Maybe author misunderstood. Maybe I misunderstood what author meant with this picture. Look, they show that drag is greater here. Drag lift less, drag less, lift greater, and drag greater. At this place, yes, it's increased drag with respect to undeviated, unmoved elevator. It's increased. Lift increased and drag increased. But here, drag increased much more. And what it will be resulted in? It's like slow down this wing. Now let's come back to my three-dimensional picture. Once again, on one half of wing lift greater and another less, but drag here, no, it also became greater than it was, but not so significantly greater. Here it's much greater. And what it resulted in, that airplane not only, no, if we imagine that it rotates like this, no? It's not only rotate like this, it's not only make such a rotation. It's instead of normal direction of flight, like this. What it was. No, do imagine it was straight flight. Wait a second. Ой, не поместился. Так. Okay, let it be. I'll spoil everything, seems like. Whew. Great. Working. Instead of motion straight, forward like it was before you deviate the ailerons. Once again, it rotates, it moves its wing up. No idea how to draw it now. No, it's like moved up this wing, moved down that wing, and instead of trajectory, like we have seen it, moved forward, it's moving along curvative trajectory, like this. It's like rotating. In our case, it's rotating to the left. Yes, it's moved this wing upper, and not just rolling, but it changed trajectory due to changing of these forces on the wing. What do I mean? That ailerons used not for rolling really. They may be used for this complex. It's not so let's say direct motion, да, as when you're using the rudder, but also it may be used for changing the no for somehow, да, at least замучили. It may be used for yawing also. Ailerons moved both for rolling, and ailerons may be used for yawing, because using of ailerons will be resulted in distortion, let's say, of trajectory of airplane flight. There were the group of three main flight controls. And now we need to talk about additional flight controls, because what, take a look on the picture that I preliminary prepared already to here. It's a list of flight controls of one airplane. I talked to you only about three group of controls, like elevator, rudder, and ailerons. And here you see for one airplane the whole list. Let's come back to the beginning of our story. I said that usually we are changing position. We make these rotations, evolutions of airplane by changing their additional devices which are hinged, no, like piece of stabilizer or piece of rudder or piece of wing. They are separated. They design it like inserts, let's say, to the trailing edge of the wing, and they are hinged there. So they move up, down, and due to this, they change forces on the wing or on the empennage. And due to this, we elevate airplane. But it's not the whole true. The next portion of true is the whole stabilizer may move. For instance, we have no stabilizer with hinged piece. We have stabilizer that wholly hinged and wholly rotatable on the hinge somewhere inside of fuselage. In this case, it's appeared one more name. Look, it was named stabilizer. Let's type it, stabilizer. And now it's additionally combined with function of elevator. Elevator. This stabilizer and elevator together. Let's do this one, if it's possible. No, in Paint it's not possible. Okay, like this. Stabilizer. Complex word. You see, stabilizer and elevator. Stabilizer. No, the whole word, of course, like this. I divided in front of you on purpose in order you may remember this. No, like it's more easy to remember. Let's take a look onto picture. Somewhere here it was a picture. Here is. Да. Usually this used for not non-great in size airplane. What right now you see empennage, you see fin with rudder. No, this split, it means that P is really separated. That one, it's not it's it's not elevator. That one, it's the sort of trimmer. What is trimmer? It's another story. Right now, we see that whole stabilizer may be rotatable, may change its position, the whole stabilizer, no? Angle of attack of all the stabilizer, not curvature of stabilizer, but the whole angle of attack of all stabilizer may be changed during the flight. And this thing is called stabiliator. Somewhere else it was given in the picture. Maybe let's come back to the flight controls to see it. Вот это вот. Да. Stabilizer. Here is the picture that you have already seen, similar one, which I took. It's control system of elevator, and here is, you see, it's not hinged piece. It's the whole stabilizer rotatable with respect to the longitudinal axis of airplane. And here it's explained something about this stabilizer. It's not the only hybrid. We will see later. Right now, come back to the story about. Right now, let's see one more picture. Just here. Да. Three main type of control surfaces you see. Black one, elevators, either up or down. No, they shown proper position and respecting motion, no, resulting motion. They show like center, no, not center of gravity. No, yes, it's easy to imagine for us center of gravity, but really in flight it's supported by lift. Okay, let's think like this. It will be more easy for us. That forces momenting with respect to the center of gravity. Of course, it will be much easier. That center of gravity, it's like point of support, but really in flight it's not like this. And on this, with respect to this point, we imagine all the forces acting to the airplane. Here you see the work of ailerons and resulting motions. In contrary to what I drawn in my picture, I drawn this right one was down and left is up. They did it in contrary. That is why motion in another side, quite clear. And the vertical rudder. Vertical stabilizer rudder. Vertical stabilizer name, once again, fin. The same name like fin of fishes, for instance. Fins of fishes, also easy to remember for you. Next, flaps, slats, spoilers. What is it? Let's come back to a story about flight. We have horizontal flight. In horizontal flight, to provide stability, we use stabilizer and fin. To provide controllability, we use elevator, rudder, and ailerons. And in takeoff, while takeoff and landing, how to make airplane either climb or descent efficiently. Once again, do recollect this formula. What we may control. We understand that during takeoff, let's talk about takeoff first. During takeoff, speed, it can't be so high right now. Yes, we are yet running on the runway and we are increasing the speed. But we do remember, in order to realize takeoff, in order to take off from airfield, we need lift much times, sometimes greater than the aircraft weight. It means really at this moment we need huge speed. much more speed than speed of horizontal cruise flight. Now, let's imagine that this thing, area of wing, is not controllable. It's not to be changed during the flight. That is also not true. But do imagine that it's not changeable. Do imagine. And we may change something in this area of formula. That is why we talked about these aerodynamical coefficients and so on. Aerodynamical coefficients which we have seen in these pictures. Let me to show you once again. These aerodynamical coefficients. I'm talking about Cy, Cx, coefficients of lift, coefficient of drag. How we may change it? By changing the angle of attack. One way. No, in case of stabilizer, yes, it's work. In case of the whole wing, especially for big airplane, it's engineering, mechanically complex decision. It's too much. Yes. So if we're not able to move all the wing, change all the wing, maybe we're able to change, no, like it was some area of the wing in shape, in order to change curvature in this place. Yes, such decision exists already for more than 100 years. And such decision, name of this flight control is flap. Flaps are typically, now as they are, we need some another color. No idea which one. Is it different? Not much. Okay, that one. A bit different, I hope. From all the colors I used, no, not much else. Or whatsoever. Let's use. Flaps typically placed, yes, on the back side of the wing, where closer to the root of wing. And this, sorry, in this area. And the same is here. Flaps. Why flaps? No, because on the right, on the left. Flap. No, I mean, why flap? Flap. Why I'm not saying anything at all. Oh, awful. Flap. Да что ж такое? What happened? Кошмар. Flaps. Not bright color. And flap is, maybe we need to remove all this. And to draw airfoil. Flap is the movable portion of wing trailing edge. But to be frank, it may be up to 30%, not trailing edge, but the 30% of the cord of the let me to draw this. It's our wing, and its original profile to be like this. And flap will be somewhere here. It's maybe not long. It's maybe, as I said, you up to 0.3 horda cord. No, as it was designated like little b, let it be little b in our picture. And what you may do to this flap. Flap always move only down, but while takeoff, flap moves in position up to approximately, it's different for different structures, up to 15 degree. Of course, it's much more, much more in my picture. Sorry, it's not 15, quite clear. And while landing, the same flap also move down, but it's moved down up to 30 degree. No, I show you the upper values, actually quite clear that it comes about some range. And why I draw these values like this, in order you to remember, it comes about twice more during landing. So flap used in similar way seems like during takeoff and landing, but it's moved down only and moved on different values for takeoff and for landing. Now, what it resulted in when you change the shape, I hope you understand. The more plane shape or the more curvative shape. The more curvative shape, it means that you have these coefficients of lifts what for comparatively plane shape like this, and for a more curvative shape, you will have it even greater and far alpha crucial. Alpha critical will be far. Very well. But is it just rotatable and that's it? No. Quite clear that no. By now, exist no, half of dozen of different decisions, and right now we will see their shapes and names of these engineering decisions. And what we need also to remember. I hope you do remember what is possible when we increase angle of attack significantly. Let me to once again remind you those pictures that we have seen yesterday. Oh, like this. Now, these two pictures we need. That is so-called laminar flow, and here we have flow separation. Flow separation, it's very dangerous situation because it's resulted in the sharp reducing of lift. So what if we rotate the piece? No, as I said, we change curvative, practically we change something like angle of attack, general angle of attack, let's say, no? For this flap. For the wing, not the flap. No, and flap itself, we change angle of attack of the flap with respect to the wing. I hope you understand that piece of flap, it's changed angle of attack, and it was notable that angle of attack for us, it's important characteristic because it's maybe resulted in such flow separation installed, no, at least partially on the flap, and instead of rock for our benefit, instead to increase lift, flap may reduce lift. So in case you use just movable flap, where is it? Just movable like this, hinged and movable, you are limited in these angles. You are not able to move it much. No, you're able, but it will be resulted in bad sequences. You shouldn't move it much. They are, of course, limited in aircraft structure. You can't move it more than predicted by no, by designer at all. But you are limited in these values, and it means that you can't increase the force significantly. Whether any way to control this boundary layer here, no? By some way, in order to prevent this fluid separation, whether any way to laminarize the boundary layer somewhere on the petiole area of the wing. Well, yes, and there are even structures of wing. No, you can't know it maybe right now, but the whole device is hidden in the wing, which are responsible to laminarize the flow over the wing in order to prevent some undesirable phenomena and to reduce drag. Quite clear that in this case, even if it's not stall yet, if it's just turbulization of the boundary layer, it's already not good, let's say, because you increase in drag. Increase in drag, it means that you are spending more fuel to provide the same motion forward. You will be forced to increase thrust and to increase fuel consuming because to provide the same motion, you need more thrust, and more thrust because you have greater drag somewhere or on the wing or somewhere else. And in order to check the time, I need to watch the time to time. We have special laminarizing devices. For instance, it may be organized the additional downwashing, let's say, of some area. For instance, you have some device inside of wing which downwash additionally here. It's like add some little jet streams here appeared in order to laminarize downwashing in this area, in risking area. Or in contrary, it's maybe some something like vacuumizing devices, like sucking devices, which responsible to pull these streamlines closer to the surface of the wing. What I'm talking about, that is the reason for appearing of these various structures of various structures of flaps. No, the main, as I said, half of dozen, you see, plain flap. Plain flap is just hinged and moved all the piece, all the trailing edge you see here. Next one. Давайте, let's, oh my phone. It spent much when we use this Google Meet, when we use something to record. And internet actually comes through the phone, because in our home, internet, in our building, internet, wired internet, it's yet absent after beginning of war. So all the internet is mobile. Так, and look, plain flap, you see, the whole piece rotatable down. That is split flap. In our language, we call it щиток, something like little shield. And this shield, it's a portion really of cross section which move down, but top surface it's not not spoiled yet. So it's provides the curvature here, but quite clear that at this place it's reducing the pressure in this place, and as a result, here is the turbulization of downwashing streams, and it's not much feasible, let's say, kind of flap. No, anyway, they exist. Slotted flap. What is different with respect to what? Look at this slotted flap and this plain flap. What is different with respect to it? You see this arrow symbolize that air comes, air may downwash this area additionally, air squeeze through this gap, clearance has appeared. And it means that design of flap, it looks like specially designed like this, that it does not coincide ideally when it's deviated. It's already do not coincide ideally to the shape of the all other wing, and through this slot that appeared, you do remember that potential energy different. You know that water comes where to the more lower place. Agree, where potential energy is less, to position with minimum potential energy. In our case, under the wing, pressure is more, and over the wing pressure is less. And that is why if you give any slot here, pressure will of course squeeze through the slot to the area where pressure is less. And due to this, it's downwash additionally this flap and laminarize the downwashing the boundary layer in this area to prevent that. Where is it? To prevent this dreadful situation with flow separation. So that one may be more effective than plain flap in terms that it's able to be rotated to the greater angle to change curvature more significantly. And as it's more significant changing of curvature, it means that that one is able to give more more coefficient Cy, more lift. I hope you understand it. That one, so-called Fowler flap. Look what happened. What happened with respect to the normal flap. Take a look. Where was original place of this piece of metal, this piece of trailing edge? It was somewhere here. Let me to steal this picture for a while. And let's try to and here is. Where was this piece originally? Let's see. It was here, and it was no, it's not possible here to rotate it to some angle in freeway. I hope you understand. It was in more flat position, and it was somewhere here. What does it mean for us? Do pay attention once again to the formula. This Fowler flap, what it's responsible for with respect to what was originally, it's increased the area of wing additionally. It's like moved back a bit, and due to this it's increased this value, and due to this, no, besides of changing of coefficient Cy, it's also responsible for additional increasing of the area of the wing and additional increasing the lift. Great thing, yes, but even more even more great thing is this one, slotted Fowler flap. That is mechanically extremely complex thing, and here you see two links of the flap, like two pieces, but really it's maybe three and even four. Typical decision is three for big airplanes, and next we might see it in photos of airplanes, I hope. And this slotted Fowler flap, on one hand, it's increase curvature. It may increase curvature significantly, much more significantly than plain flap, because you have these slots, and these slots they resulted in better downwashing of this area during changing of shape. And moreover, such a flap, you see where was its original position. Area of wing was approximately finished. No, the end of wing was approximately somewhere here, and that one increased significantly the whole area of the wing. All this is made with one purpose: to increase lift during takeoff or landing. No, why we need to increase lift during takeoff? It's quite clear. But why we need to increase it while landing? What is the idiotic idea? Let's take it yet somewhere in the side of our memory, and let's see what another type of device which may help us to increase lift. Besides the trailing edge, we still have leading edge, and it's not busy yet. Yes, and no, it's not involved in this process of increasing the lift. So in order to increase lift, we have so-called slats or movable leading edge, it's called. In different literature and different sources, you might find different names. So typical name is slat, or besides of slats, movable leading edge. And these movable leading edge or slats, they work with no, in very similar way as flaps. What mean it's work? It's moved down, and generally it's resulted in changing the curvature, like temporarily changing the curvature of the airfoil during the takeoff or landing. No, and it's responsible for changing of this coefficient of lift as a result. Moreover, similar story like it was with flaps. Let's come back to the pilot handbook to see design decisions. Fixed slot, so called. It's just moved down to change curvature. That's it. Here you see this no, movable slot, like it's moved a little bit front. It's like slide a bit here. And somehow it's similar to the Fowler flap in this meaning, you understand? And here is you see something what leading edge flap, as it called here, no, at least in this book it's called like this. You see rather similar to the split flap decision when bottom surface it's partially moved down, but still it does not affect on the top surface of the airfoil of the wing. One more decision is here, what they call leading edge cuff. And all these devices, whether flap or slats, they necessary. No, here it's at all called fixed slot, movable slot. It's a fixed slot slat maybe, and movable slot slat must be, or leading edge high lift devices. You see, even third name is appeared already for these devices. No, as I said, you this one, this book, as far as I remember, as far as I understand, it's not so-called native English speaker wrote this book. But whatever the book is as a whole is great enough, very good book. And once again, during takeoff, it's clear lift we need to increase because we need lift much greater than weight in order to realize takeoff. Why we need to increase lift while landing? Very weird. Let's see. What is landing? Landing is descending and slowing of the airplane and stopping of the airplane after some way on the runway. You need to stop. And in order not to use very long runway, quite clear, before you touch down the earth, before you touch down the runway, you need the speed, the general speed of airplane as little as only possible. What does it mean as little as possible? No, the less speed, the better, because you stop short in shorter runway while landing. The less speed is better. Yes, the less speed is better. Or do you imagine that somewhere on heights, pilot reduce the speed on heights at least 200 meters? What happened to airplane? And that is not cruise height. It means that not cruise altitude. It means that it's very short time for reaction of the pilot in case of any occasional factors intruding to this landing. Side wind, forward wind, rear wind, no, whatsoever, weather conditions, and airplane reducing the speed like stone, no, not like stone, of course, but some ballistic trajectory improved by, additionally improved by these aerodynamical surfaces, falling down to runway actually. It will be very stiff landing, if not even crash, but very stiff. Uh, Dangerous for passengers, for crew, for cargo, and for airplane structure itself. Not each landing gear is able to stand with to such loads. So the task during landing is to keep lift as high as possible when speed you need to reduce significantly. In idea that next you need to stop at all. To keep lift and to provide airplane normal descending, gliding as it called, while landing, might help you those flaps. But together with keeping lift, you have another idea in your mind. I need to stop quickly. And for this, we may do what? We may use one more force. We have here the force of drag, and when cruise flight, do forgive me, when cruise horizontal flight, it was hazardous force, it was unpleasant, we don't like it. Now, during landing, we like it because it may help us to stop sooner. No, we may stop at some moment safely. What do I mean? Lift we need to increase to provide safety of landing, and this one we need to increase not for safety but to reducing the speed of runway, no, not runway, no, да, running along runway, and to reducing the time of this running along runway after landing, after touchdown. And what we will do right now, maybe it's necessary to do pause in record in order files will be not so great. And once again, flap is necessary. Flap should help us uh, to solve both of problem. That is why while landing we deviate flap down, but we deviate it on much more significant angle on purpose in order to increase drag either, to increase lift, to hold lift, to keep lift value for safety landing, but to increase drag either. And one more device which will help us in this task to spoil lift. It's called spoiler. No, about spoilers and other things we will talk after after I make a pause to reducing the size of file for you.